Hi everyone, my name is Agnishom and today I'm going to tell you about hardware accelerated matching of regular expressions with counting. This is joint work with my friends Alexi and Lincoln, who I suppose are in the audience. So here we have a story. A detective has returned from some adventure and they have 200 MB of text and they're looking for something formatted like an address, and the team thinks it's hopeless. But fortunately, some ninja thinks that they know what to do and they come swinging on a rope and they say that there are no regular expressions. So what are regular expressions? They are some kind of formalism to specify patterns in text. So let's say we want to search some text for email addresses. We could use something like this. This part of the expression says that we are looking for something alphanumeric. This part says we want one or more of something alphanumeric. And this is how the regular expression matches the text below. Now let's say we want to look for credit card expiry dates in a format like this. We have month and then the year, but they're separated by a hyphen or a slash. So we have this vertical bar over here, which denotes a disjunction. So this string is matched by the expression as follows. I have color coded the part that matches the expression. So regular expressions also appear in other contexts besides just simple text processing applications. For example, we have Snort, which is a network intrusion detection tool, and it uses regular expressions maintained by the community to do this. And an antivirus software called ClamAV, it uses regular expression signatures, and there are over 4,000 of them in the database of this antivirus software. Finally, bioinformatics people also use uh, regular expression. This ProSite database is a database of protein motifs. So how do we match regular expressions? This is what we do on software. We turn the regular expression into a non-deterministic finite state automata, and then we compile it into a deterministic finite state automaton and get something like this. However, this method could result in an exponentially large automaton in the very last step. Another method is something like this, where you turn a regular expression into a backtracking parser. However, this might take exponentially large time to match certain worst case inputs. So between these two methods, we have a space versus time trade-off. Another method which is not that talked about is matching directly on hardware ASIC. So here we have a non-deterministic automata, and we are going to directly simulate this on an ASIC called the Automata processor. So the Automata processor was originally introduced by a company called Micron, and it's very fast because it simulates non-determinism directly. The Automata processor can simulate multiple active states, and since this hardware is massively parallel on each of these states, it can parallelly compute transitions independently. So this overperforms CPU-based matching by around a factor of 256, and also certain GPU-based matchers by a factor of around 32. So regular expressions sometimes have this feature which I will call counting in this talk, and they make regular expressions more succinct. So here we have a regular expression that supposedly matches a phone number. It's formatted with dashes. So we have three digits and then a dash, and then another 3 digits and then a dash, and another 4 digits. We could just abbreviate it like this using counting. So this is meant to say that the regular expression before is repeated 3 times or 4 times. Another example is the credit card expiration date. So instead of having this regular expression repeated 4 times at the end, we could use curly braces 4 to denote that we are looking for a 4-digit number. And these expressions are ubiquitous. Around 33% of SNORT, which is the network intrusion detection software, they have counting in their expressions. And over 50% of pro-site motifs have used counting. How can we match regular expressions with counting? Well, the simplest approach is to just unfold them. So if we have Rn, we can simply write them out as R concat R n times. And then we have a usual regular expression, and we can use any of our previous methods. However, when we do this unfolding, we lose the succinctness that was provided by the counting. So when we do this on hardware, this means we need more area for the chip and possibly also more consumption of energy. So I would like to talk about how we can match regular expressions with counting on hardware ASICs without losing succinctness. To do this, I introduced this construct called Automata with counters, which I will abbreviate as NCA. So these are like finite automata, but they are also equipped with counters, which can be initialized when certain transitions are taken. And sometimes they are incremented. And we also have these guards which check whether a certain condition is satisfied. So for example, in this case, this guard is meant to say that this state can only be accepting if the value of x is equal to 4. So this regular expression here is supposed to see some number of a's and b's, and then it is supposed to see exactly 4 c's, and it does so by initializing a counter to 1 and counting up to 4. So here I will try to demonstrate with an example how an NCA would actually match a string. So I have the NCA from the last slide, and initially I have a token over here, because this is the initial state, and the string seen so far is just the empty string. We have not encountered any characters. Let's say we see the letter A. This transition in which I have highlighted with blue is taken, and this token remains where it is. Now, let's say we see the letter C. This transition moves the token from the previous state to this state, and this initializes the counter X to 1. Now I see another C. This blue transition is taken again, and the value of X is incremented to 2. And if I see another C, this can be incremented to 3. And finally, if I have incremented it to 4, this guard is satisfied. So I can mark this string as accepted by the automaton. So now I have a regular expression which is slightly more problematic, as we will see. The purpose of this regular expression is to accept a string whose fourth last letter is A. So it sees some number of A's and B's, and then it sees 4 letters. Any of the last 3 of those 4 letters could be anything, but the first of those 4 letters has to be an A. So here the automaton tries to guess when this transition has to be taken. This is why this is particularly non-deterministic. I will explain this with an example of a run of this automaton. So again, I have this automaton. Initially, I have a token over here. So now let's say I see the letter A. Both of these transitions will fire. And this is perfectly fine with us because our hardware is able to simulate multiple active states. In fact, this is what the purpose of the hardware was, to be able to simulate multiple active states at once. And right now we have 2 tokens, one in the first state and another one in the second state, because both of these transitions were taken. Now let's say we see the letter B. this token moves from the second state to the third state, and the first token remains where it is because the transitions highlighted in blue are taken. So at this moment, since the second transition was taken, we have initialized the value of this counter to 1. If we see an A, we will be firing all of these transitions actually. So we will be firing almost all of these transitions, not the one in the middle because there are no tokens here. So these are the transitions that are fired right now. So this transition puts the token from here to here, and this transition keeps this token where it was. And finally, this other transition, it increments the value of X. So now I have another occurrence of B. And here what happens is this token from the second place to the third place, it initializes the value of the counter to 1. But also we have a transition from the third place to itself, which increments the value of the counter from x equal to 2 to x equal to 3. So at this moment, we actually have two tokens at the same place, or rather two different values of this counter at the third place, which have two different values. This is a situation which I will call counter ambiguity, when tokens at the same state can have different values. And this could be a problem for us because if we use simple counters, we will be able to store only one of these values. So we need to be able to tell when this situation is occurring. So if we want to correctly simulate NCA, we need to be able to keep track of both of those values or be able to tell when such a situation is occurring. And these are the questions we answer in our work. Firstly, how can we detect when this situation, namely counter ambiguity, is going to happen for a given expression? And when we do have an expression with counter ambiguity, how can we address the situation and how should we match that expression? So detecting counter ambiguity. Detecting counter ambiguity is NP hard. When you have counting constraints that are very large in orders of magnitude, this problem might become intractable. However, in practice, these constraints are pretty small, so it's not that much of a problem. We developed an exact analysis technique. And in this technique, if you have an expression where the largest counting constraint is of the value of the counting constraint is size n, then this expression might take up to time n squared. And this works by constructing the product automaton of the automaton with itself. We also have an over approximate analysis. This analysis is oblivious to the size of the counting constraints, in the sense that it does not take more time if the value of the counter is larger. So if the regular expression is size m, then it takes m squared, disregarding the value of the counters. However, in some cases, this will give you false positives. Here I have a table showing how frequently counting expressions occur in realistic data sets and how often are they counter ambiguous. So from the second column, we see that counting expressions are indeed fairly ubiquitous. So in the Automata dataset, for example, around half of the expressions have some form of counting, and indeed all of them exhibit counter ambiguity. So this shows the significance of this problem in realistic expressions. Now we would like to answer the question of how can we deal with this case when the expressions are indeed counter ambiguous. So this is the situation we had from the previous slide. we had x equal to both 1 and 3. And I propose that it is useful to represent these situations with bit vectors. So I would, instead of just storing a single value of the counter, I would store a bit vector of length 3, since 3 is the upper bound for this counter. And here we have a bit vector of length 3. We have ones at x equal to 1 and x equal to 3 because those are the values that are present in this set. And this indeed helps represent this more succinctly, and it is a better idea in practice than to use in additional states, because states take up more area than representing a bit vector. And incrementing these bit vectors is easy. So on the left, we have a bit vector which represents the set 1, 3. If we shift that, we get the set representing 2, 4. So this represents incrementing all the values of the counter at once. And this is simply a shift of the bit vector to the left. We have some empirical results which show that this method can actually be used to save area and energy. So on the bottom, we have the size of the counting constraint, and the column on the left talks about counter unambiguous expressions. In these expressions, since the expression is counter unambiguous, we can use a single counter to represent the particular value. And when we do this, we see that since only a counter can represent the value that is required, the area or the energy is constant. However, if we did use the unfolding technique, we would use linearly as much area or energy. In the counter ambiguous cases, it is not possible to use a counter because because on certain inputs we may have to represent more than one values of the counter. And this is where we use the solution from our last slide, which is the bit vectors. And in this case, we see that the area or the energy do in fact increase linearly, and this is expected to happen. However, even though this improvement is not asymptotic, we are still able to see that we are saving some area or energy. Let's summarize. Non-deterministic automata can be used to model regular expressions. And when we try to implement these in hardware, we might see a particular phenomena which I call counter ambiguity. And we have designed a mechanism of analysis that helps us detect counter ambiguity. When regular expressions are indeed counter ambiguous, we use bit vectors to represent counter values. And finally, we have shown empirically that this approach does indeed help save space and energy. Thank you for listening. I am happy to take questions. Yes.
Hey, Nishant, good talk.
Thank you.
I got two questions. So the first one is, if we discard the counter completely, right, then I think you pointed out on one of your first slides that, there's a linear translation from regular expressions to NFAs and an exponential translation from NFAs to DFAs. Right?
Yes.
But if you have multiple states activating at the same time, isn't this essentially a subset structure determinization?
Yes. So I say that the approach by the hardware is some kind of So Senthil is asking whether this approach is essentially the subset construction. Is that the question?
I'm asking whether you have the hardware approach, which has the multiple states activating, is essentially this, right?
Yes. So maybe I can paraphrase the question a little bit. So there is a construction called subset construction, which is essentially the conversion from non-deterministic automata to deterministic automata. It looks like that. So I think Senthil's question is whether this is the subset construction, and essentially that is true, because what this NFA processor does is it maintains subsets of states which I call active. And the nice thing is that it is able to compute the transitions on every active state independently, which is a benefit you do not get from a software simulation usually. So in this sense, even though this is a subset construction, it's a little bit more efficient.
I see. And then, thank you. And my next question would be, okay, so bring the counter back in. How can we ensure that we don't do something pathological, like simulate a two-counter machine or something like that? Is there any guard against that?
Yes. So Senthil is asking about two counter machines, or basically we know from automata theory that when we have counters, these machines can be enormously powerful. And since we are able to have something that actually works, how can we possibly do something so powerful? And the answer is we don't do something so powerful because in these expressions, the counters essentially have a bound because they are coming from regular expressions, and we use the upper bounds in these regular expressions to have upper bounds in the counters. Besides, the power of two counter machines, for example, if I'm not wrong, that comes from being able to compare two counters. We don't allow comparison of counters. We allow zero tests. I mean, we don't need to do zero tests, but we allow testing if the counter value is something, but we don't allow comparison across counters.
Do you allow counters to decrement?
We don't decrement.
Okay, I see. Cool. Good work, man.
Thank you. Yes.
Maybe I missed it. So for the detection part, you just check if the vector is like has more than one position that have one, or
Yes. So if I am not wrong, the question is about how do we check if something is counter ambiguous. So we basically we unfold this NFA with counters to a normal NFA, and this loses succinctness, but we only have to do this particular check once. So this is not done during the matching, so the unrolling part is fine. And the ambiguity checking works as follows. We construct the product of the NFA with itself, and then we check whether there is a reachable state, where you have two different values of the counters. So nothing too smart, it's really like an exploration of the state space. Thank you for the question. Yes.
Is the detection of the ambiguity done on the hardware or is on the software?
It is done on the software side. So let me explain. I think there is a confusion about like when the detection is done versus when the matching is done. So there are two phases to this process. Like we first would like to do whatever analysis needs to be done on the regular expression. And then when it is done, we put it on the hardware so that the hardware can match whatever expression it wants to on whatever string it wants to do. But we are, since we potentially this matching process takes very long, so we can afford to spend more time during the analysis part, so that we do this analysis part only once before the matching starts, and that's when we check for our ambiguity. And once we have figured out whether it's ambiguous or not, we decide whether we will use a counter versus whether we will use a bit vector. Thank you. Other questions? Yes.
Great talk. This is a very practical question. How does this work? Like, are you using FPGAs in practice, or what are you using to actually implement these in hardware?
Thank you. So the question is about whether we are using FPGA or how the hardware really works. So I believe FPGA-based solutions have been tried. They work actually faster than CPUs and GPUs, but this particular approach is not based on FPGAs. These are based on hardware ASICs, and this is a chip that is specifically designed for simulating NFAs. And this, if you want to look up more on this, you can look up Micron's Automata processor. Does that answer the question?
Yeah, so I guess the other side of my question is this like this isn't a programmable thing. This is something that you prepare the regular expression you want to do, you burn it into the chip, and then you're done.
Yes, it might be slightly programmable. You might be able to load another NFA into it, but you can't do arbitrary logical things like an FPGA. You can only load NFAs into it. Thank you.
One last question on Zoom from without.
Does the number of processors have to be larger than the number of states in the non-deterministic automata? I am not sure what VTOM means by number of processors. So I'm thinking of the entire hardware which simulates a particular NFA as a processor. It is able to support a certain number of states, like there is an upper bound. I don't know how much that is, but it can't be unlimited. Does that answer the question? Thank you.
Okay, everyone, I think we should thank Agisha.
Thank you, everyone.